So let us further discuss the interrupt behavior in Cortex M4 in addition to interrupt grouping. So as we had discussed previously, we had seen the registers also. Interrupts can be enabled or disabled. Interrupts can be in a pending state or it may not be pending. Interrupt can be active or inactive, and the nested vector interrupt controller is designed to support peripherals that generate pulse interrupt request as well as peripherals with high level interrupt request. Okay, so this is about how the interrupt lines are being asserted. Sometimes interrupt lines will be interrupts will be accepted at, for an active high, for an active low, or a level triggered interrupt. Okay. Now for pulsed interrupt requests, the pulse duration must be at least 1 clock cycle log. That is, whatever is the clock speed of the controller, say it is running at 100 megahertz. Okay, so the pulse duration has to be 1 upon 100 megahertz, right? So that is the duration of your pulse. So the pulse duration cannot be smaller than that. For level triggered interrupts, the peripheral requesting service asserts the request signal until it is cleared by the operation inside the ISR. We will not see level triggered interrupts much, so we will only be talking about edge triggered interrupts. But had there been a level triggered interrupt, the level would have to be cleared by the software inside the ISR. So that's the programmer's job to clear the trigger. Now the pending status of the interrupts are stored in programmable registers in the NVIC. We saw that. We saw the registers, exact registers which actually store the programmable, the pending status of the registers. The pending status means it is put to a state of waiting for the processor to serve the interrupt. So the IPSR registers in the NVIC hold the pending status of the interrupts, as we saw just now. Okay. Now coming to, so we will see a set of timing diagrams here as to how a single interrupt would behave in different scenarios. Now this is very important because when you have to debug certain problems with interrupts, or when you wish for an interrupt to behave in a particular way, you have to know about how the interrupt behaves. So this is a simple scenario where you have an interrupt request coming in and the hardware sets the pending status. But before the interrupt can be serviced, so this is the interrupt status. So before the interrupt can be serviced, the user, the software, that is you, have decided to clear the pending status even before the interrupt has started processing. So basically what happens here is the interrupt is never executed. The interrupt is cancelled. Okay, so this is one behavior. Second behavior is, suppose there is you are making an interrupt request which is, say it's a level triggered interrupt. Okay, so you have asserted the interrupt for a longer duration of time. So it's a long duration of time, not a short one. And so the moment an interrupt is asserted, the processor is going to raise the hardware is going to raise the pending request. Now and we know that we can anytime disable the pending request. So say the user disables a pending request here. Nevertheless, since the interrupt request is high at that point, it's still high, the hardware will raise it back again to pending. So as long as it is high, no matter what you do, the pending status is going to keep getting high as long as the interrupt request stays. If the interrupt request goes, then it is going to be like the previous scenario here. The interrupt is never going to come. But nevertheless, in this case, it's a different scenario. The duration of the interrupt request is higher, longer rather. Now, this is another scenario where you constantly keep the interrupt request active. Okay, so you don't lower the interrupt request. It is active indefinitely for whatever reason. Maybe a line has got stuck. Say maybe, you know, there has been some error and an interrupt is constantly getting fired, or somebody wants it to be this way. So for whatever reason, the interrupt request is constantly getting fired. It's a constant high throughout. So the interrupt pending status goes high here, and the interrupt starts getting serviced. So the interrupt gets serviced here, and the same ISR, the ISR completes at this point. The moment the ISR completes, since the interrupt request is indefinitely high, again a pending state is raised and the interrupt is entered again. So if the interrupt request stays active, this interrupt is going to be entered repeatedly. Once it completes, it's going to go back and enter again. So, and this keeps happening as long as this interrupt request stays active. So this is another behavior of the interrupt. Okay, the third behavior is the interrupt is asserted, there is a pending, and the interrupt and the ISR starts executing here. As the ISR starts executing, before this ISR interrupt service routine completes, another interrupt comes. The same interrupt is requested again, the same one. Okay, so what happens is, when it is requested again, the pen bit goes high and the same interrupt is executed again here. So what happens, if you request the interrupt within the execution of the first interrupt, the same interrupt is going to get executed after the first run completes. You could have thought this as a complete separate request, because if this bar was to this side, suppose this interrupt was completed and you would have raised it somewhere here, the behavior would be the same. In this case, what happens is, the interrupt is entered again after waiting for the first part to complete. So it is not that when this interrupt is requested, the interrupt gets preempted from here, the execution is broken and this one starts from here. It waits for this to complete and then this one continues. Then this one is raised again and it happens to execute. Another scenario is multiple interrupts are asserted within the pending state. So say 4 or 5 or 6 times you are asserting within the pending state before the actual interrupt ISR starts executing. So basically what happens at that point is, all these are considered as one interrupt and the interrupt is going to execute once. That is because all these interrupts have been asserted before the interrupt started. If any of this got asserted after this interrupt had started, then that would be considered as a separate request. Now this is so we spoke about interrupt preemption and interrupt priority grouping and so on. This is just a diagrammatic representation of how interrupt preemption happens. So you already know this, we discussed about this, but this is how it looks. So say interrupt 1 of a lower priority is executing, so is asserted here. Once it is asserted, so this was a thread running, that is maybe your main program is running at this point and interrupt comes in, first interrupt 1 comes in of a lower priority. You do not know that this interrupt is going to come in at that point. Okay, so event 1 occurs here and then stacking for interrupt 1 starts. So we will see stacking and unstacking in detail in the upcoming slides. So interrupt 1 starts executing here. Okay. So interrupt 1 is executing here and then the second interrupt comes in, which is of a higher priority. The moment that happens, interrupt 2 event actually stops interrupt 1. Interrupt 1 is stopped and the stacking starts for interrupt number 2. Now There's a very specific reason why I have made the length of stacking between this area and this area different. This is not a mistake. The stacking is different for a particular reason, which we will see later. Okay, there is a, because for stacking with floating points active, the stacking duration and the size of uh, the stack is much higher as far as stacking with floating points are concerned. So I just tried to show that here. And then interrupt 2 starts executing. Once interrupt 2 executes and finishes executing, interrupt 2 returns. Then interrupt 1 completes, interrupt 1 unstacking completes, and then the thread is resumed. So this is how interrupt preemption happens. And this, of course, has everything to do with the interrupt grouping and subgrouping that we saw previously. Coming to tail chaining is an interrupt behavior where suppose you have an interrupt of some priority executing, and another interrupt comes which is of the same or lesser priority than the interrupt that is currently executing. So if the interrupt currently executing has a priority of say 7, the other interrupt may have come with a priority of 8 or 7. Okay, so 8 means lower priority, higher number is lower priority in the case of ARM Cortex. In such a case, we know that the interrupt is not preempted. The first interrupt is not going to be preempted. Rather, the first interrupt will complete execution and then the second interrupt will start executing. Now, between these two interrupts, when the first interrupt completes execution and the second interrupt starts executing, once an interrupt completes its execution, there is an unstacking process that happens. The stack frame is restored. Whatever stack frame was saved before the interrupt execution is restored back into the registers. Now, if another interrupt comes in, and as I mentioned, of the same or lesser priority, if it were of a higher priority, then there has to be a preemption and stacking of the second interrupt. But this is a different scenario. Here, it's the same or lesser priority. So, of course, the first interrupt will have to do an unstacking, and the second interrupt on entry will have to again do a stacking. But the unstacking and stacking would be of the same set of registers, because obviously it has unstacked the registers. The second interrupt will have to take the same set of register values and stack them again. So stack just grows back, stack just extends and contracts, and it's pretty much the same thing. And of course, stacking and unstacking is an expensive operation as far as latency is concerned. So what ARM Cortex does is it totally skips the stacking and the unstacking phase because it is not useful. So it enters the second interrupt directly. And in this case, for a memory system which has no wait state, the tail chain latency from one interrupt to the other is only 6 clock cycles, which is pretty good. So this is tail chaining. Now lazy stacking is again something interesting. Assuming that you have the floating point unit enabled. Now if floating point unit is enabled, the stacking and the unstacking process is more extensive than the floating point unit being not enabled, because a lot more registers need to be saved onto the stack for floating point unit. However, say even if you would have enabled the floating point unit but then not used any floating point operation, so you enabled the floating point unit but your code does not utilize the floating point registers, neither does it do any floating point operation, it just leaves the floating point unit alone. What happens is and if an interrupt comes in at that point, the stacking happens for the shorter number of registers, because Cortex M4 detects that no operation happened for the floating point registers. So why stack them and waste clock cycles? So it just leaves the stacking of the floating point registers and goes ahead with the shorter version of stacking. So this again saves a lot of clock cycles. So tail chaining and lazy stacking is actually to reduce the interrupt latency in Cortex M4.